There's a very important rule that comes into play when you're looking at radicals, and sometimes you need to write absolute value symbols where there were not originally absolute value symbols. And you need to know when to do that and when not to do that, because there's only a particular time when you have to do it. So here's the rule. You can write this down. When there is a variable inside the radical, so it has to be a variable, a letter. This doesn't apply to when numbers are inside the radical, but when there's a variable inside the radical and there is an even index, that means square root, fourth root, sixth root, something like that, it has to be an even index, and the variable ends up coming outside the radical with an odd exponent on it. In other words, the final answer has like an x with a 1 power to it, or an x with a 3 power to it, or an x with a 5 power on it, then, and that comes outside the radical, then you have to put absolute value symbols around that variable and its exponent. So let's look at an example on the next page. So here's an example that meets all the qualifications of the page before. We have a variable under the radical, inside the radical, and then we have a index that is even. Remember, a square root has an understood index of 2. A lot of people think it's an understood index of 1, but if you think about it, what does square root mean? It means what's squared will give me the number underneath the radical, and so an understood 2 is there, and the reason they started dropping off the 2 index is because square root's the most common used root, and so they decided just to not write the 2 every time, but there's an understood 2 there, so that is an even index. And then what happens is, if you think about having 3 x's underneath a radical, you need 2 before it can come out, and you have one guy that has to stay in. And on the way out, one always goes away and one stays. You can watch my prison break video, and I'll explain that in another terminology. But anyway, so that's what we have going on, and the 2 has to stay inside because he doesn't have a pair of 2's to be able to come out. So he's going to stay inside, and so is one of the x's. So we have a 2 that stays in, and an x that stays in, and an x that comes out, and one that goes away. And so that's what we end up with. Now, this is the scenario where if you don't put an absolute value on the number outside, or the variable outside, it will actually be wrong. And so we've got to know when we need to do that. So think about what the exponent would be on this variable that's on the outside. It would be to the first power if you had to write one. And that is an odd exponent. So we had all the qualifications. We had a variable under the radical, we had an even index, and we had an odd power on that variable when it came out. So therefore we need absolute value bars. And some of you may ask, why in the world do we need to know when to put an absolute value on it and when not, and why would we even need one in the first place? The reason we need one is because it wouldn't be true all the time without one. And let me give you a scenario, and maybe this will make sense. If it doesn't make a whole lot of sense, don't worry about it. Just memorize the rule on the front page, and you'll be good to go. But for those of you that like to understand why, let's go about why. So what if x, the thing is, x is a variable. That means it varies. We don't know what it is until somebody gives us a value for it. And so what if x happened to equal -3? Let's see if we left off the absolute value, if the original problem would actually equal x times square root of 2x. So putting in the -3 in all the x spots, we have 2 times -3 to the third power. And then on the other side, we have -3 for that x, and then we have 2 times -3 for that x. So those two sides should equal each other if that's a true statement. So we're trying to figure out, is this true or not? Well, let's work out the left side. The left side is 2 times -3 to the third. -3 to the third exponent comes before multiplication, so you'd have to do -3 to the third is 27 negative. It's negative 27 times 2 is negative 54. So you'd have a square root of negative 54 on the left side. And then on the right side, we would have 2 times negative 3, which is negative 6. So we'll put a negative 6 under here. And then we have a negative 3 on the outside. Now, if we were to break this guy down, we would have a negative 1 under the radical, which is this part would become an I. We have a pair of 2's, which would come out as a 3, and you can multiply it by the I. And then inside the radical, we would have a 2 and a 3 that would have to stay inside, and 2 times 3 is 6. So that would be the simplification of the square root of negative 54. Now let's look at the other side. We've got a negative 6. That would be a negative 1 times 2 times 3. If we broke that down, the square root of negative 1 is I. And then 2 and 3 are single, so they would have to both stay in, and you'd have a 6. And then there's already a negative 3 out here, which would get placed in front of the I that we took out. And we have basically a statement that says that 3i square root of 6 equals negative 3i square root of 6. Well, that's just not true, because 3 on this side and negative 3 on this side do not make those equivalent statements. They were almost alike, but that one little part messed it up. And so we could do all kinds of examples, and you would see that sometimes, depending on what x is, if it's negative, it might actually not equal each other. Sometimes, if it's positive, they won't equal each other. It just depends on the type of problem. But the point is that if you don't put an absolute value on the x, then you will not get the right answer. So if I put an absolute value then all the way back here on the x, now let's see if it's true. So if we put an absolute value on this, we get positive 3. And so, because the absolute value of negative 3 is positive 3, well, that changes this to a positive 3 now, which changes this to a positive 3. And then you have 3i square root of 6 equals 3i square root of 6, and it's true. So it wasn't true until we added the absolute value bars. And so remember, again, you don't have to completely understand the why, but that is why we have to write it, because it's not always true if we don't write the absolute value bars. So this is the answer to number 1. So here's another example. Again, we have a even index. We've got some variables under the radical, so this may be a situation where we need to have absolute value bars. Let's first break it down into its prime factorization so we can kind of see what can come outside the radical and what has to stay in. Okay, this is what we have all broken down. I know there's shortcuts to this, but I just want to visually show you what's going on. With a fourth index, we need a group of 4 before it can come outside the radical. So here's a group of 4, and that comes out as a single 2. And then we're done with that group. Then we have a group of 4 x's, so an x can come out for that group. And then we've got a group of x's, so there's an x that can come out for that group. Then we have a group of 4 y's, and so a y can come out for that group. Another 4 y's and another 4 y's, so 2 more y's can come out. Then we've got this leftover y. We didn't have any leftovers in the 2's or the x's, but we did have a leftover y, and the leftover y has to stay in. So that's kind of what we've got going on. So let's kind of tally them up. And this is 2x squared y to the third, and then there's a y underneath here. So, do we need absolute values, and if so, where? You know, we had the first 2 qualifications, that it was a even index with variables underneath the radical. Some variables came outside the radical, and only the ones that have odd exponents on them need the absolute value. So sometimes you'll have both variables have absolute value bars on them. Sometimes you'll only have one variable that needs the absolute value bars, and the number will never need absolute value bars. It would actually be wrong if you put them on. So you need absolute value bars around the one that's a variable with an odd exponent, but not the variable with the even exponent. So this would be our final answer. Finally, we can look at this last one. If we broke this down, it would be 4 2's and 3 x's. And we need groups of 3 before they can come outside the radical. So here's a group of 3. We put a 2 outside the radical, and that's a cube root radical. And then we have 3 x's, so we can put an x outside the radical, and that's an x to the first power. And then the leftover 2 has to stay inside the radical. The reason we don't need absolute values on this, even though it was to an odd power, is because one of our rules didn't happen. One of our stipulations didn't happen. It was not an even index to begin with. It has to be an even index to begin with, and if it is an odd index, that trumps everything, and you do not need the absolute value bars when it's an odd index. So even though it turned out the way the other one, the very first one we did, in that x was to the first power, which is an odd power, and it was a variable, and it was a variable that was inside the radical, you don't have to put absolute value bars on that because it was an odd index, and so the rule just doesn't apply. And we could do an example. You could try different values for x and see if they turn out to give you this answer every time, and they will. If you put a negative number in for x, you'll get this answer. If you put a positive number in for x, you'll still get this answer, and no absolute value bars are needed. The very last thing I need to point out is sometimes they will use these words in the instructions: assume all variables are positive. If they ever use that wording, assume all variables are positive, you do not ever need absolute value bars. And the reason is because the thing that usually was messing up the whole thing that needed the absolute value bars is the fact that we didn't know if x was negative or positive, and so we didn't know, the answer would not be correct unless we put absolute value bars on the variable. But now they're saying assume all the variables are positive, so no absolute value bars will be needed. So in other words, if you get those instructions, then you can forget about the whole absolute value bar thing, and this is a even index. It does have a variable under the radical that's going to come out as a single x to the first, which is an odd exponent, but we do not need absolute value bars only because they take away that need when they say assume all variables are positive. So we'll put an x out here, and we'll also put a 2 out here, and we'll keep a 2 and an x inside, and our final answer is just 2x, square root of 2x. No absolute value bars needed because of these instructions.